it's the last session of the day and everybody already tired, and so I will try to make the talk lighter and minimize the amount of code I'm going to show. And also the whole motivation for this talk is not about code that I have written or somebody else written, but it's about what kind of code we want to write and how to go about it. And there are two motivations for this talk. So the first motivation is the message that was posted on a Camel mailing list on March 2024. So it says, well, assume this following Camel code that has side effects, can we automatically transform into something that in this using suitable monad and put it on. So, I mean, that's a kind of natural questions, and well, what kind of bothers me is that it's appeared so natural questions to so many people. Because there's two things that bothered me, one of them immediately. So you see there's a put 5 plus let fx and so forth, so forth. And what you see now in the second part of the code, there is a bind, there is a do, IP, and so forth. Is it really that monadic code is so much better, so much readable than the code we had before, such that you really want to transform the format to the left? So that's my immediate motivation. I was kind of couldn't believe that people were asking for it. But there is a second point to this, and I will come to the near the end of it. So there is a second motivation, which always, often come from the student questions of, talking to students. So we have a seminar with the students, and one of the things they have to do is to write the code for list permutation and obtain all permutation from the list. And I'm positive everybody, done this. And there is nothing inherently complex. It's a very simple, but it's called a little bit messy. And that's why it makes a very good exercise for the students, so to do this mess. But if you heard of a functional programming language, is called it, functional logic programming language, Curry, and if you ever looked at the standard library of Curry, then you'll see this code for obtaining list permutation. Well, Curry has a Haskell-like syntax. So it says the permutation is a fold R of insert over the empty list. So takes the list with the empty list as a 0 and performs fold of insert. And insert is the function that non-deterministically takes an element, takes a list, and insert this element somewhere into this list. And this question mark is the choice operator into the Curry, and the rest of it is kind of standard notation. And if you saw this code once, you probably can't forget it. It's so elegant code, right? And it also tells a lot about, because it's fold R insert empty list and it grows progressively longer, it immediately follows that a number of permutations that are stored to the length of the list, right? So it's such a nice code. And wouldn't it be nice if we can write this code in both Deva studying OCaml? We can write something very similar to OCaml. And of course we know how to, if we have a insert here as a non-deterministic function that has a choice, and how we deal with non-determinism, well, we write code in a list monad, and well, I try to explain this algorithm using a list monad. And I wrote some code, but of course the result wasn't like fold R insert something, so there was a little bit monad binding and so forth overhead involved. And that kind of bothered me. Well, I tried to explain to the student, and they didn't seem to buy my explanation, and especially maybe looking at all the overhead that I kind of get from the impression that they're not satisfied. And it bothered me that how can we actually write something very similar? And working one night, I actually realized that we can do something very, very, very similar to that code, and we'll see, very, very similar. So we wanted to write all permutations find all permutations of the integer list. So let's build a language that lets us do exactly this thing. So we have a problem, let's build a language for that. Well, in our language we have integer list form, so we have integers. Well, we need to have operations, so we need to have a data type, int t, so it's a representation, integers in our DSL. And we need integer literals. Well, generally speaking, we need more operations on integers, but for permutation of integer lists, we don't actually need to have any operations on integers. So if we need it, we can add them later. So that's in the style that I'm writing, it's tag with final style, we can add operations later. So for now, we don't need any operations, we just leave it there. Of course, we need to deal with lists, integer lists. So we do, in a very similar way. So we define a type lists are represented in DSL. So we need nil and we need cons. Well, list, it's kind of not necessarily needed, right? Because lists can be represented cons, so nil, but as we know, it's very convenient to have notation for literal lists. And of course, we need to have a deconstructor. Now, the deconstructor is a little bit, well, I mean, it's always, when you do embedded languages, it's always the problem, right? Deconstructor, it always becomes ugly. And so the first argument is the list, and if this list turns out to be empty, then it invokes second argument that passes forces the thumb, and if it's non-empty, then it invokes the third argument and passes the rest and the console. Well, if we are talking about lists, then it's nice to have a fold operation. Well, it's not necessary to have fold. It's expressible in terms of already, but it's also convenient that we add to the language. And finally, because we wanted to have non-determinism, well, we add two operations on the non-determinism. We add a fail, and we have a choice. So choice takes two expressions, and non-deterministically chooses one of them. So that's the semantics. And given this definition of the language, so this is the module type, it says which operations are there in the language. We can write list permutation. So it says at the very beginning, so it's parameterized by some implementation of our language. So the signature and that, it says this is some, gives that implementation, gives this how all the primitives are implemented, what particular type is implemented. But the rest of the code doesn't actually care about implementation. And as promised, permutation is fold R insert nil. Exactly like in curry code. Well, insert is almost exactly as in curry code. With some, I mean, a decon was, annoying. Well, just the other week, last week, I think that Jeremy sent me a message that said there is some very nice PPX extension that he developed that you can write this decon in a more, in a match style library. So that problem can be solved. Well, I've been using this style for many other things, for example, for embedding SQL and embedding other languages, and invariably there is one reviewer that says, well, all this module and this M is kind of ugly, can we get rid of the modules? Well, yes, you can do without, that argument. So you can have first-class modules. So if you disregard the first two lines, then the rest of the code, it's exactly, look exactly as OCaml code, standard OCaml code, there is nothing there. And even those two lines can be beautified. So if Jeremy's and OCaml Labs multi-core OCaml, that module implicits and clear lines gets into OCaml, then we don't actually have to write this modular and that O and fun module. So this gray part will disappear, and it becomes almost as regular OCaml code. So, and especially if you decon can move out decon. So it all can be done. Let's look again at the code. So there is one interesting part of it. So I defined integers, I defined integer lists, right? But I didn't define any there is no function types in this language, right? So there is a types for integers, type for integer lists, and there is no type for functions. So our DSL is first order. And I said that fold R can be expressed in terms of decon, and so we need some kind of recursion. And that's what the reviewer, one comment to the reviewer says. The paper says our DSL is not the lambda calculus, is essentially first order. And it says, but previously it was said that fold R could be defined from what was shown in the slide. So if there is a contradiction in that. I think it's a very excellent question from the reviewer, and I want to thank him for doing this or her. Well, it's a very good point to contemplate. So if there is a contradiction, so both of them are true. So yes, there is a language is first order, and there is no. You can define fold R. And actually, if you look at the source code which comes with the language, then you can actually see the implementation. So it's actually true. Another thing to look at the index. So there is a fold R, right? As I said, well, there's obviously arrows in there, so there is some kind of functions. But again, there are no functions in the meta language, so which functions are those? Well, in this case, the functions, they're OCaml functions. So OCaml acts as a sort of a macro, right? So we have a first-order language, and OCaml builds the computation in this first-order language, but OCaml is void by God, the high-order language, and has lots of convenient functions, has functions. So we have a very fancy macro system, and so that fold R is a high-order macro, and insert is also macro, and it's also recursive macro. So they actually not only have macros, they have a recursive macros. And surprisingly, all works. Yes, you can actually, try it out and see how it all works. So eventually we need to have to run, yes, now we come to running it, so eventually we need to have an implementation. And one of the implementation, because we're interested in all permutations of the list, then, well, list monad is the one. So int list is an integer, so it's a list of possible integers, and ilist is a list of possible integers. And I don't write the rest because, I think it takes you, faster to write this code than for me to explain it. So I skip this one. And they're easy to think about extensions later on. So for example, there is a function in Perl, it's called RAD. I have no idea why it's called this way. So if you have a predicate and you have a non-deterministic computation, it kind of filters out all the choices that do not satisfy the predicate. And there is a predicate, once it says if there is a computation that has more than one answer possibly, that just pick one of them, non-deterministic, and forget about it. So it expresses don't care non-determinism. And using this extension, well, as you can see, it's Antagoras final. We include the previous earlier signature, and we just add two more operations. And in our language, we define the function sorted. It's a standard function tested, is sorted. And then we can define function. It's called slow sort in functional language. It's a very good benchmark how to sort a list very, very slow. It takes obtain all permutations of the list and remove the ones that do not, not sorted. And because the list has duplicate, there actually may be several choices. Then just choose one of those choices because the ones which is actually a very good standard benchmark in functional logic programming. So now I kind of come to the more, so that's essentially all of the code. Come to the more philosophical part. So this is the phrase from one of the reviewers. So it says it's all just an OCaml implementation of their algebraic theory. And I agree with it. From that point of view, it's indeed, there's nothing, I'm not proposing any new algebraic theory, any new algebraic treatment of effect. So in a sense, all this talk about how to write it nicely in OCaml. So I fully agree with this quote. But my first reaction, I should be frank, so my first reaction when I read this paragraph was, I remember once I read a column in long-defunct magazines called Unix Review, and it was from the author who used to write documentation for now called the defunct Sun. And he said that once he was walking into the office, and he realized that all the multiple volumes of API Sun documentations can be reduced to just one single phrase. Apply appropriate function to appropriate arguments. So yes, at this level, if you take high enough level, all the documentation refers to this thing. And so at this level, I fully agree with the reviewer. Well, but we are talking about monads. So of course, monads are very, useful thing, and so because they let us uniformly. Once we lift language in right monadic syntax, we can instantiate any monad we want if it's done fully morphical. And of course, it deals with the high order functions, and we don't actually have a functions. So I agree that's a far more general solution. But there is one, I wanted to make several points about it. So one point is that, indeed, if we wanted to have, well, monad is a fully general notion of computation, and indeed, it works great. But in our approach, we didn't needed any function, so actually even not a high order functions or any functions at all. So maybe if we try to, take a different approach, so we have this problem, and let's see if we design a solution that fits the problem. It turns out in many cases, then the language itself can be first order. rather than, and the meta language will provide all the conveniences that we, wanted to have. So that partition of the, well, of course it doesn't have, cover all the problems, but it covers many interesting problems. And to justification as to what, is it true or not. So lightweight modular staging, for example, right? So they implemented many DSLs, and I asked TR what sort of languages they're building, because I had questions about how the function. He said, well, most of the languages that we build, they're actually first order. So it turns out it's surprisingly wide enough. So, but there is another point. So we instantiated language to the list monad because we wanted to find all permutations of the list. But suppose we wanted to say compute size of the terms or something like that. So we can instantiate, well, in the first approximation, int t and list t, both are type integer that tell the kind of size of the term, and some gives a measure how term they are. If we wrote this language monadically, then we should provide, of course, pure and bind. Well, pure seems to be easy, but the bind will have this signature that seems to be kind of odd, right? So it's function, so it's kind of hard to see how to implement this function. But there is another implementation which you can find in the accompanying code. So, for example, I want to generate a code. So instead of not just compute the own permutations of the list, I want to compute a function that, well, when compiled, will produce all the permutation of the list, of the given list, or some list that reads from there, some locations. So I want to do code generation. So because I want to do code generation, in that case, I would say int t would be int code, and ilist would be ilist code. Actually, int list code and list code, so it would be code. So if we wrote this list permutation monadical and say, let's instantiate monad. Well, we cannot instantiate in monad, because if it were monad, we need to find a function bind with a signature. But there is no such function, because, well, you kind of think about what it means. So it takes any code, and you run this when it gets the value of like alpha. So it kind of means that you have to run alpha code. But this is a code that you generate later. You can't actually run it right away, right? So, so therefore, alpha code generation actually it's not monadic, it's applicative. But it's actually not applicative either, because look at this pure function. Pure function says, given any value, we can create code of this fashion. Well, suppose, as I said, we wanted to generate code, store it in the library, and then compile later. When you store it in the library, it's essentially text file, right? So if you pure says, take the OCaml function, and store in a file code of representing this function, well, that's certainly kind of not going to work, right? So it's pure is not polymorphic over alpha, which is conventional monad interface requires. In our language, it's okay, because we only operate integers, so we say which literals we actually want, and for them we can, we can run this implementation. So that is another point, that not committing ourselves to monadic interface, I just say, well, here's the language and why are we implementing it. It turns out later on we can instantiate, have implementation which are not monadic, not applicative, or some of them not even clear what they are. Finally, when I mentioned this approach on a camel mailing list, Yara Minsky said, well, it's nice if you have types and that tell you what the computation is. Well, for monadic representation, you can look at the type and say if it's a monadic value, then it's effectful, if it's non-monadic, it's pure. But exactly the same holds in here, right? So if you look at, if the type of the expression says int t or ilist t, so it's represent our DSL. Our DSL is monadic, and every volt, which is non-deterministic potential. But everything else is deterministic. So if you look at the function insert, then, well, it deterministically computes non-deterministic computation. Well, that's what it is. So, so that was been just an experiment to see how far we can push and how much we lose and how nice it might look or might not look. And it was at the first it wasn't clear if I can manage to get rid of the functions in the DSL, especially in this implementation where does the code generation. There's some very non-trivial part which I completely skip. But it turns out it is possible, which is, I mean, it was somewhat surprised to me. And it may be used more, made to look as it's used in curry. And yes, it's surprisingly simple, and well, if you don't commit ourselves to monad, it turns out maybe more implementations can be done. The one that we present. Well, I think it's time. Okay, thank you. You had comments?
I'm not sure I understand the high-level picture.
Well,
what are you trying to do?
Well, I'm trying. Okay, so I'm trying to do so.
Sorry.
What can we do? How much code we can write effectful code, which we do not commit ourselves initially to any monadic implementation. So we wanted to write effectful code. And we wanted to write in a way where effects, so in not a monadic style, so without binds and returns. So it's a most natural style. Yes, and yeah, indirect style. And one point is that it gives you more implementation because it turns out we have implementation which are not monadic at all, like code.
Yeah, it could be algebra.
Well, maybe, but not monad, right? So so.
Let's go with which one?
Okay, so yeah, okay, so we need to write.
I'm not that review.
No. But even in this case, as I said, pure operator, right? Pure is not polymorphic.
No.
So you can define, you can inject only specific types, but you cannot inject them polymorphic. So it's not a monad.
It's an algebra.
Okay. But I mean, my point is beginning, right? So it's not a conventional monad. So
No, it's an algebra.
Oh, okay. In that case, I agree. So I mean, what the signature of the language is algebraic signature.
Yeah, exactly. Yeah.
There's a question in the back.
Yeah.
Well, it's not a question, it's the other kind of a brain reviewer comment. So, if you look at Reynolds' idealized algol,
Yeah.
it had this same property where you had a comparative wild language and then a lambda calculus over it.
Okay.
And Stephen Weeks and Matthias Fleisen wrote a very nice paper where they show you could split the evaluation into two stages.
Yeah.
Where you evaluated all the lambda terms and then you'd be left with a residual
Yeah.
file program. So this looks very similar.
Yeah. I mean, yes. So it's kind of it's experiment of how far you can push and how well it works. Well, I mean, obviously there are cases when there is interactions. So we all know there are cases, but I mean, well, and then we need to have a general solutions. But just as experiment, and how far and this is the last line I actually pointed out. So if somebody says, well, here's the code using LWT, that's what I actually wanted to see. How far, I mean, how much of LWT code, async code, can be written in this style?
I have a question. So if you have a monadic API or monadic interface, I have a good. Yeah. So if you have a monadic interface, then I have a good intuition on how effects can depend on effects before them. If you have an applicative interface, I have a good intuition for how effects can depend on the results of the effect. In this model, what is the intuition behind the kind of dependencies I can have between effects and effectful?
Well, generally, I think Ohad could come in and say it because I had to say it's just algebra, right? It's algebraic theory, so this is the. Well, I mean, it's not laughing. It's actually that's exactly what it is, right? So it's intuition how to combine things. I mean, so this gives you the structure of the computation without saying. Suppose there is a meaning to these primitive expressions, and this how expressions, big expressions, put together from the simple pieces. And then it all depends on what would the meaning of the simple pieces are. Right? And the OCaml is kind of a macro says, well, I mean, we don't know what the meaning of the simple pieces are, but we can, a systematical abstract and perform substitution and so forth. But yes, it depends what the interpretation of the primitives.
But if I have a monadic interface, I don't need to know anything about
Well,
the
but-
effect to know.
But it might not necessarily, well, as I said, that, I mean, you know, in this case, it might be a code generation, so it's not any effect propagation, right? So you don't even do any effect, so you just generate a code. So the computation which it runs, it generates the code, so it doesn't do any effect, because all the effects will be on the non-determinism of the code which it generates, right? So if you had this intuition, this program runs and does some effects, this intuition would fail if you think about it as a code generator. Or, for example, there's another interface which you're thinking about, I mentioned that, for example, you wanted to do a distributed computation, right? And that all this non-determinism, it actually launches threads for each operating system, forks threads and then combines it, which is also another valid implementation of the interface. And if you think about, it's a sequential monad propagates that, so this implementation, your intuition would fail because it generates lots of, okay.
Thanks very much. Let's thank Oleg again.